Welcome. Today we will delve into a story that could have forever changed the course of World War II, about how American engineers and designers faced the critical need to quickly provide their troops with reliable shelter in the Pacific theater. 3 weeks after the attack on Pearl Harbor, bases in the Philippines and Wake Island were flooded, tents were destroyed, and hospitals were overwhelmed with pneumonia and fungal infections. Standard wooden barracks required too much time and resources, while metal structures were either too expensive or too heavy. At the same time, the British experience with semicircular metal Nissan huts since 1916 seemed promising, but their heavy steel panels and the need for a foundation made them unsuitable for the tropical climate of the Pacific. Could American industry develop a lightweight, quickly assembled, climate-resistant structure that combined the advantages of British solutions and met combat requirements? And what if, in January 1942, American engineers had already begun working on a fundamentally new type of shelter capable of changing the course of the war? That was their gamble, not just solving the problems of time and cost, but radically changing the defense strategy. Are you ready to see who and how created that very revolutionary design? Then let's begin. In December 1941, America's world collapsed in an instant. On the night Japanese bombers attacked Pearl Harbor, the fate of millions of Americans changed forever. The walls of their homes, their familiar cities, their everyday lives were destroyed in minutes. But perhaps the most urgent challenge that arose at that moment was the need to quickly provide protection for those heading to the Pacific Front. A protection that had to be reliable, fast, and at the same time, accessible. In wartime, when every second counts, standard construction methods seemed too slow, too heavy, too costly. After the attack on Pearl Harbor, when the shock and the loss of ships had not yet been recovered from, and rear services were already working at full speed, the housing situation for American troops worsened to the limit. 3 weeks, just 3 weeks, separated the start of the war from the urgent need to house tens of thousands of soldiers who had already stormed islands and planned further operations. But what could be done when bases in the Philippines and Wake Island were under the onslaught of the elements? Water, which was supposed to be a protection, flooded tents, destroyed temporary structures, turning them into a heap of debris. People forced to take shelter in improvised hideouts faced a new enemy: pneumonia, fungal diseases that spread rapidly in damp and unsanitary conditions. Each night became a test, and the number of hospitalizations grew exponentially. Standard solutions, wooden barracks built from familiar materials, seemed unsuitable for rapid response. They required time and resources, which were catastrophically scarce during wartime. Metal structures, although more durable, proved too expensive and heavy to be quickly and easily transported to the site. As a result, every attempt to build something quickly turned into a prolonged and costly process that could not provide the necessary amount of shelter in such a short time. History suggests that during World War I, the British already faced similar challenges. They introduced what were called Nissan huts, semicircular metal shelters used starting from 1916. These small, lightweight, and relatively quick-to-assemble structures proved to be a real breakthrough. They could be set up in a matter of hours, creating temporary camps and bases in various conditions. However, further research revealed that despite their versatility, Nissan huts had significant drawbacks. They used heavy steel panels that required foundations impossible to install quickly and easily in the Pacific environment. Their design proved too vulnerable to climatic tests: heavy rains, humidity, tropical heat, and storms. These structures, despite their rapid assembly, could not ensure the durability and comfort needed for long-term use at the front. Engineers and designers faced a daunting challenge. Could they create something based on British experience that combined the advantages of quick installation, lightness, and resistance to harsh climatic conditions? Could they develop a structure that wouldn't require heavy foundation work, wouldn't be too expensive, and could still provide protection and comfort for soldiers in tropical heat, rain, and storms? This question became not only a technical challenge, but also a psychological one, since the solution would determine not only the effectiveness of defense, but also the fate of human lives, their comfort, and even survival. It was at this moment, in January 1942, that a new chapter in the history of field shelters began. American engineers, armed with analysis, evidence, and lessons learned from past mistakes, set to work. They understood that it was necessary to create a fundamentally new type of shelter that could change the rules of the game. A shelter that could be installed in a short time, lightweight, climate-resistant, capable of withstanding combat conditions, and, at the same time, not cost an exorbitant amount of money. All of this was to be achieved in a context where every minute counted, and each structure had to serve as an invisible shield for those fighting for freedom. This challenge marked the beginning of a new era in military engineering. Time has shown that determination, innovation, and courage are what can change the course of a war. And it was these qualities that led to the emergence, in January of the following year, after extensive experiments, testing, and improvements, of the first prototypes of new shelters capable of truly revolutionizing the field. They not only altered the perception of rapid construction, but also offered hope that even in the most difficult conditions, it was possible to create a defense that would save lives, ensure safety, and provide soldiers with moral reassurance. Thus, a new chapter in the history of military engineering began, a story that could, in the future, change the entire course of the war. In the early 1940s, America was on the brink of changes that would not only transform the face of the war, but also rewrite the rules of construction and engineering thinking. At the heart of this revolutionary wave was a figure who had remained in the shadows until then, Buckminster Fuller. His ideas about mass-produced housing, which seemed fantastical at the time, began to take concrete form, becoming not just a dream, but a real strategy capable of altering the course of events on the front. He promoted a concept in which houses and shelters were not unique, individual masterpieces, but elements of mass production, comparable to automated car manufacturing. In his view, mass construction should become not a luxury, but a standard, accessible to everyone defending their country. The idea was to use lightweight, prefabricated, factory-made structures that could be produced on automated lines, quickly transported, and assembled just as rapidly in the field. This seemed like science fiction for the 1940s, an era when most shelters were still built from heavy wood or brick, and technological and material resources limited the possibilities for rapid response. However, despite its seemingly utopian nature, the United States already had the first experimental samples of such solutions. These were metal farm sheds, industrial hangars, and modular metal structures used for various purposes, from grain storage to equipment housing. These structures had already proven their strength and versatility, and most importantly, their ability to be erected quickly. Their experience and technological potential could serve as a foundation for developing new, more complex, and military-specific shelters. It was only necessary to adapt these principles to the realm of combat structures, which was a logical step toward innovation. The key moment came in March 1942, when a special team was formed in a small town on Rhode Island. It included top engineers, architects, factory construction specialists, and military engineers familiar with the conditions of the Pacific Theater of Operations. Their task was ambitious: to develop a shelter concept that combined ease and speed of assembly with high resistance to extreme natural conditions. It was no easy challenge. In wartime, when every minute counts, a technology was needed that could quickly respond to changing frontline situations, providing protection and safety for soldiers and civilians alike. Inspired by the experience of American farms and industrial enterprises, as well as by British Nissan huts, small prefabricated metal structures used during World War II for housing troops and equipment, these engineers began turning ideas into blueprints. Their concept involved replacing heavy wooden or brick foundations with lightweight, self-supporting metal arches. These arches had to withstand extreme weather conditions, be quickly assembled on site, and offer maximum flexibility in design. The key task was to create a system capable of providing shelters for dozens or hundreds of people in a short period, without requiring complex installation work or heavy machinery. But the main question facing the team was, could American industry implement these ideas? Would factories, accustomed to producing cars and household appliances, be able to adapt their lines to manufacture these new, revolutionary shelters? After all, it was not just about production, but about establishing new standards and methods of mass construction that could change the entire strategy of military logistics. Time was pressing, resources needed to be mobilized, and technological problems had to be solved on the fly. Every decision could be decisive, from material selection to logistics, delivery, and assembly. All of this was happening in the context of a global war, where each day could be the last for hundreds of thousands of people awaiting protection. Soon, this team would move on to work on a truly revolutionary development, capable of changing not only tactics and strategy in military construction, but also the entire concept of defense. Their ideas, born in laboratories and on drafting tables, took on a tangible form that could set a new standard. It was not just another project, it was a challenge to the existing order, an attempt to break stereotypes and harness technology that could save lives and alter the course of the war. Although many trials, doubts, and technical obstacles lay ahead, it was then that the spark was ignited, which would later grow into a true revolution in military construction. Time was passing, and the team already felt that behind their backs were not just blueprints, but the future fates of millions of people trusting them with their safety and hope for victory. In that fateful spring of 1942, when the world was still shrouded in the shadow of war and the hardships of global conflicts left their mark on all aspects of human activity, a new idea was born at the heart of the scientific and technical front. During an era when every minute could be the last, when speed, weight, and cost became not just numbers but decisive criteria, a team of engineers and designers began working on a project that promised to revolutionize the approach to creating arch structures. These people knew that they faced not just an engineering challenge, but a battle for the future, for the ability to quickly and efficiently erect durable, lightweight, and cost-effective structures capable of withstanding the harshest conditions while remaining mobile. Time was limited, requirements were strict, and the stakes were incredibly high. In this context, in April of the same year, they embarked on developing a new design that was to become the pinnacle of engineering thought. A new arch system, capable of serving as the foundation for numerous strategic facilities. The development process began with defining key parameters. The engineers had no room for error. Every decision had to be precise, every move carefully considered. During the tough working days, when the glow of a lamp cast long shadows over tables covered with blueprints, and the air was filled with the sense of grease and hot metal, the team delved into an endless series of iterations. Their methods were not traditional. Instead of relying solely on static calculations and standard technologies, they implemented innovative approaches that were decades ahead of their time. Rapid drawings were used, and prototypes made from lightweight materials were created, unafraid of mistakes and miscalculations. Fast fabrication of parts allowed them to model structures in mere hours rather than weeks, enabling immediate testing, identification of weak points, and adjustments. This approach was akin to flying a jet in a world where most engineers still relied on slow, labor-intensive design and testing cycles. The size of the panel chosen for the new structure, 16 feet wide and 20 feet long, was no coincidence. It was a deliberate decision, dictated not only by transportation and assembly requirements, but also by the internal logic of the idea itself. Such dimensions allowed panels to be transported manually, without heavy machinery, significantly reducing installation time and costs. Each panel was like a puzzle piece. It had to fit perfectly into the overall structure, becoming part of a unified, durable, and lightweight frame. The radius of the arch, 8 feet, was also no random choice. It was calculated to provide an optimal balance of strength and internal space. Within this radius, there was not just a geometric formula, but an entire strategy to ensure the stability of the structure with minimal material costs while maintaining the ability to accommodate necessary equipment and installations inside. Simultaneously, active development of connectors was underway. The key innovation lay in abandoning internal supports, which allowed for a significant reduction in the overall weight of the structure and faster assembly. These connectors had to be strong enough to withstand not only static loads, but also dynamic impacts, such as shocks, wind forces, and storms. The designers had no room for error. If the connectors failed the tests, the entire concept would collapse like a house of cards. Therefore, highly sophisticated prototypes were created in their laboratories, subjected to numerous tests simulating real operating conditions. The first prototype was assembled in May, just a few weeks after the work began. Time was a critical factor, and even with such a tight schedule, the engineers succeeded. The assembly took just over 14 hours. It was a real breakthrough. It proved that their approach worked, that ideas embodied in metal could become reality, and most importantly, that such structures could be quickly reproduced and scaled. Following this, improvements were made. Through careful analysis of test data, engineers managed to reduce the assembly time to 8 hours. This opened new horizons for rapid construction during wartime, when every minute counts, and each hour could save lives or provide a strategic advantage. But a crucial question faced the engineers. Could these experimental samples withstand the impacts of natural disasters? Pacific storms raging across the Pacific Ocean spared no one and nothing. Their power is not just wind and rain. It is a destructive force capable of destroying even the strongest structures. Would the new panels, developed using revolutionary methods, withstand these tests? The question became not only technical but also strategic. After all, if the technology cannot withstand nature's trials, all efforts will be in vain. The stakes are not only the reputation of the engineers, but also the fate of a project that could set a new standard in rapidly deployable structures capable of resisting any natural calamity. At this moment, when it seemed that everything depended on the tests, the engineers began large-scale testing. They knew that confirming reliability was not just about numbers and protocols, but proof that their ideas could save lives, ensure safety, and lay the foundation for the future. Time is passing, and each test brings them closer to an answer, whether their innovative structures can spark a new revolution in engineering. For now, all that remains is to wait, observe the preparations, and sense that something greater than just another prototype awaits them ahead. They were awaiting confirmation that bold ideas, supported by thorough experiments and relentless perseverance, could change the world. In June 1942, against the backdrop of a global military conflict, not only alarming news about battles and strategic maneuvers was heard for the first time in a long while, but also incredible technical solutions capable of altering the course of history. In a situation where each day could be the last for millions of people, and where resources were limited and time the most valuable and scarce resource, engineers and designers began creating unique shelters capable of providing reliable protection in the harshest conditions. Their task was not only to develop a structure that could withstand the enemy, but also to create a system that would enable mass production of these shelters and rapid delivery to where they were needed most. This challenge became a true test of engineering ingenuity, logistics, and strategic thinking. And it was here, in the heart of the military-industrial complex, that a revolution began. One that would change not only the technological landscape of the time, but also the balance of power on the front lines. In the first months of their work, the team of engineers not only sought solutions, but also painstakingly gathered facts that would later form the basis of their final masterpiece. In June 1942, the final design was developed, consisting of exactly 96 panels. Each panel weighed less than 50 pounds, an unprecedented feat for that time, as most structures required significant effort and resources for transportation and assembly. These panels could be assembled in just a few hours, only 8, which was revolutionary compared to traditional methods. The entire structure covered an area of 720 square feet, allowing it to shelter a whole group of people or house necessary equipment. Such scale, however, did not increase weight or complicate transportation. Everything was carefully thought out so that every second and every effort was used efficiently. One of the key elements of this system was the decision to abandon wooden flooring. In wartime conditions and with constant relocations to different theaters of combat, wooden bases became a weak link. They required additional time, effort, and resources for installation, and were vulnerable to moisture and pests. Engineers decided to eliminate this drawback by creating a design that could stand directly on the ground or on a specially prepared platform. This was a fundamental shift. The structure now rested not on wooden or metal frames, but on specially designed steel pins. These pins were anchored either into the ground or onto wooden platforms, allowing shelters to be installed on almost any surface. This approach not only significantly reduced assembly time, but also decreased the overall weight of the structure, making it more mobile and versatile. A crucial task was to ensure comfortable conditions inside the shelter, especially in tropical climates where humidity and high temperatures created additional challenges. Engineers understood that without proper ventilation, the structure could become a source of problems. Condensation, high humidity, and hot days would turn the shelter into a trap. Therefore, they began upgrading the ventilation systems. Specially designed vents and openings were added, which could be easily opened and closed depending on the weather and needs. These elements provided continuous air exchange, eliminating condensation issues and maintaining a comfortable temperature inside the shelter. Experimental tests demonstrated that such systems could withstand tropical rains, and the flow of fresh air created a sensation of coolness even on the hottest days. The foundation of the structure became another important component. Steel pins, anchored to the ground or wooden platforms, allowed for quick assembly and disassembly of the shelters without much effort. This was not just a technical detail, it was a key to strategic flexibility. The structure could be installed on any surface, whether a flat field, a hill, or even damaged buildings. Such a universal approach enabled rapid response to changing combat conditions, delivering protection where it was most needed. Alongside development and installation, active testing of new solutions was underway. Over 2 months, a team of engineers conducted intensive inspections. They subjected the structures to storms approaching wind speeds of 100 miles per hour. Remarkably, despite their lightness and mobility, the structures withstood these tests without any damage. Wind gusts whistled around, crackled and roared, as if confirming the power and reliability of the new system. Eyewitness accounts and precise measurements showed that even under extreme conditions, the shelters maintained their integrity, did not deform, and did not collapse. This was a true breakthrough, confirmed by facts and analysis. However, as with any complex technical system, problems arose. Corrosion was the main enemy of metal structures in humid and tropical climates. Engineers quickly found a solution: hot dip galvanizing. This process coated the steel elements with a protective layer that prevented rusting and preserved the metal's strength for many years. Special corrosion-resistant materials were also used, which not only extended the lifespan of the shelters, but also reduced maintenance and repair costs. All of this was done considering the need for mass production, since millions of such structures were required to be quickly and widely deployed to the front. The question that constantly faced engineers and management was how to ensure mass production and rapid delivery of millions of such shelters so as not to fall behind the pace of the war. Under conditions of global confrontation and limited resources, new methods of labor organization, automation, and logistics had to be implemented. It was precisely here, in this complex puzzle, that the brilliance of strategic thinking was revealed. Production capacities were scaled up to incredible levels. In a short period of time, factories that previously produced limited series of products transformed into true centers of mass production. Within just a few months, the weekly output of shelters exceeded 1,500 units. Such a pace not only met the needs of the front, but also surpassed expectations, providing the United States with strategic superiority, allowing them to maintain defensive lines and build new positions with confidence in their strength. As a result, thanks to these engineering solutions, strategic planning, and relentless pursuit of perfection, something greater than just a protective shelter was created. It became a symbol of technological progress in wartime, proof that even in the darkest times, the human mind is capable of creating miracles. Production capacities reached unprecedented scales, ensuring the country's strategic power and strengthening its position on the global stage. Every detail, every element, every idea, all combined into a powerful mechanism capable of changing the course of the war and saving the lives of those on the front lines. Evidence, technical reports, and facts all confirm that this system became the key to success, and that this was how a new era of military engineering was built. In August 1942, the world seemed to hold its breath. Dark clouds of war loomed on the horizon, and a nation gripped by anxiety had to prepare for what lay ahead. Not just battles, but a massive mobilization of resources capable of changing the course of events. This era became a time when industry, historically linked to peaceful production, suddenly transformed into a war machine. At the heart of this mechanism were powerful factories turning millions of parts into a continuous front line, and logistics that had to ensure that every shelter, every military base, and every safe haven was protected. Production capacities scattered across the country, like a living heart of a great machine, were reconfigured in August of that year. Not just retooled, but completely re-equipped. Factories in Pennsylvania and Illinois, once producing goods for civilian needs, now operated around the clock, transforming steel sheets and zinc into hundreds of thousands of panels that, within a matter of weeks, would become part of the protective system. These enterprises, like a well-trained army, utilized automated lines that resembled a rehearsal for the automotive industry. Their sounds, the stamping hum, the zinc coating whistle, the packaging rustle, created a symphony of military efficiency. Every panel, every fastener, every instruction was designed to maximize the speed of production. It was in the quiet of the factory halls that a new era was born, an era of standardization, where each shelter kit was transformed into a precisely measured, perfectly packed unit. One kit consisted of 96 panels, neatly folded, with fasteners and instructions included, and arranged to fit entirely on a single standard freight car. This simple, seemingly straightforward idea, to pack hundreds of panels as compactly as possible, became the key to large-scale military production. Each batch ready for shipment was meant to become part of a vast system covering the entire country. When, in September 1942, the first batch was sent to the Pacific Front, it marked a real breakthrough, not just in delivering supplies, but as a symbol that industry could respond quickly, scale up, and meet the front's needs with the precision of a well-oiled machine. Soon, the assembly of shelters became a standardized operation. Each part had its place, each shelter its role. The process became automatic. Workers, armed with instructions and precise templates, assembled structures in minutes, and deliveries from one end of the country to the other became routine, tested by time. Within 6 months, weekly production reached incredible levels for that time, about 1,500 kits per week. This meant that millions of panels, fasteners, and instructions were already heading to their destinations. These shelters covered bases, islands, strategic points of national defense. The entire system, like a well-coordinated army, operated smoothly, without failures or delays. The question that all managers and engineers asked themselves these days was, could this industrial system, based on standardization and automation, ensure scalability and quality? Could these factories, conveyors, and logistics chains withstand the pressure of war? The answer was clear. It lay in the fact that thanks to this system, precisely tuned and unprecedented in scale, the country could not only respond to the challenges of the time, but also surpass them. Production was no longer just a mechanism. It became a strategic tool capable of providing scalability, speed, and quality. And the more shelters were shipped, the more confident everyone became in victory. This industrial system was not just a technical achievement. It became the foundation for rapidly expanding military capabilities, a basis for dominance in the most complex and dangerous operations. And this base is the result not of random efforts, but of a carefully planned strategy in which every detail had its place and every chain its function. In this context, the main question arises: can such industrial logistics, built on automation, standardization, and precise coordination ensure scalability and consistent quality of production. After all, the outcome depended not only on manufacturing efficiency, but also on the fate of millions of lives hidden behind these shelters' walls. Time will tell whether the system can withstand the pressures of war or collapse under the weight of its own scale. But one thing is already clear. It was this power, this systemic approach, that became the foundation for rapid expansion and ultimately for dominance in military operations. It was precisely on the edge of technology and strategy, in this instant fusion of automated lines, logistical chains, and strategic thinking, that the basis for victory was laid. And this foundation was no accident. It was the result of intense work by thousands of engineers, workers, and logistics specialists. In their hands, a new reality emerged, where scale and speed became the keys to success. And the future of the war depended precisely on whether this system, built on automation and standardization, could withstand all tests of time, scale its capabilities, and maintain unwavering quality. The world seemed to understand the value of these efforts, and the future was embedded in those millions of details, packages, and chains distributed across the country. Time will tell whether this industrial machine, this colossal system, can become not only a symbol of technological progress, but also a decisive factor in victory. For now, it was moving, working, and expanding. And along this path, a new history was being created. A story in which every element, every panel, and every shelter played its role in a grand game of fate. In conditions where night turns into day and danger hangs in the air with every breath, the testing of combat shelters took on special significance. In August 1942, when tropical heat reached its peak and humidity reminded of nature's all-pervasive power, the first samples of these structures were delivered to Guadalcanal, an island that became a symbol of fierce battles and unwavering resolve. There, in the living heart of the Pacific Ocean, where temperatures from morning to evening sometimes exceeded 95 degrees Fahrenheit and humidity reached 90%, adverse weather conditions became not just a backdrop, but the main adversary. Daily Japanese bombings turned this piece of land into a battlefield where each moment could bring a new wave of destruction. And it was precisely there, amid explosions and the roar of sirens, that the real-world testing of these shelters began. A test that would determine the fate of the new structures. First of all, engineers and technicians focused on rapid construction. In 36 hours, under constant danger and resource shortages, the first bases were built, along with the shelters within them. These structures seemed to possess an incredible ability to withstand mortar shelling and bomb attacks. Witnesses reported that even during intense assaults, the concrete walls remained intact, untouched by explosions. The explosive energy that could destroy a typical building in seconds was absorbed by the thickness and strength of the materials. Even at the height of the bombing, relative silence reigned inside the shelters, and the protective structures performed their functions with impeccable reliability. It seemed like a miracle, something that should become the new standard of protection for soldiers under siege. However, reality quickly proved otherwise. Just 2 weeks after their installation, the first signs of wear began to appear. Humidity combined with sea salt penetrated the surface of the materials, causing initial signs of corrosion. Metal parts rusted and cracks started to form in the concrete. The interior spaces, intended to be safe havens, became sources of new dangers. Mold and fungi appeared inside. These microscopic enemies, initially invisible, gradually eroded the structure of the shelters, making them less reliable. Evidence showed that without timely repairs and treatment of the materials, their durability could be at risk. Therefore, engineers, armed with knowledge and experience, began working, enhancing ventilation systems, introducing new protective coatings, and doing everything possible to preserve the integrity of the structures. November of the year 42 arrived. The storm was not just a metaphor, but a real test of nature. In the tropical cyclone, wind speeds reached over 110 miles per hour, turning the sky into a roiling sea of clouds and whirlwinds. The island where the shelters were located became a battleground for the elements. The wind tore and battered everything. Trees broke, roofs were blown off, and many buildings were destroyed under nature's onslaught. But amid this chaos, surprisingly, most of the shelters remained intact. 80%. These are not just numbers, but proof of how well these structures were prepared for extreme conditions. Of the 43 structures affected by the storm, 39 withstood it, maintained their shape and protective function, continuing to serve as reliable protection for those inside. Eyewitness accounts confirm that, even under the onslaught of such destructive winds, these shelters showed no cracks, did not collapse, and did not lose their protective properties. Under these conditions, on other islands such as Ibiza, testing continued in subsequent years. There, in 1945, the shelters faced not only artillery attacks, but also storms, hurricanes, and other natural disasters. And once again, the reliability of these structures was confirmed. Explosions tearing through air and earth could not destroy them, and storms with winds up to 110 miles per hour did not break them. These tests became not only a verification of materials and technologies, but also proof that continuous improvement of designs can lead to outstanding results. The question that engineers and scientists asked themselves was, how to ensure durability and safety in conditions where natural and combat forces merge into a single stream of destruction? How to make shelters that not only withstand the initial strikes, but also maintain their protective function for many years. These tests and refinements led to the transformation of combat shelters from simple temporary structures into true defense systems. Constant improvement, ongoing testing, and adaptation to new conditions turned them into a reliable line of defense, capable of withstanding even the harshest challenges. In this process, in the constant struggle for survival, the understanding emerged. It is precisely through perseverance, scientific approach, and relentless effort that one can create a protection capable of enduring any test, be it a storm or an enemy attack. This lesson, reinforced by numerous real-world examples and evidence, remains relevant to this day. The answer to the main question, how to ensure durability and safety in extreme conditions, became the result not only of technical innovations, but also of continuous testing and ongoing refinements. These shelters, tested by time and the elements, have become a symbol of engineering genius and human resilience. Continuous testing and improvements transform them from simple structures into a dependable system capable of surviving in the harshest environments. And this story demonstrates that without a constant search for new solutions and unwavering belief in success, no design can withstand the test of time and nature. Reliability is born in ongoing refinements, relentless research, and faith in triumph over nature and war. In the post-war years, when the world was still shrouded in the ashes of destruction and uncertainty, America faced the urgent need to radically rethink approaches to housing, infrastructure, and survival. Amid this chaos and confusion, at the very heart of the country, a phenomenon emerged that, decades later, would be recognized not only as an engineering revolution, but also as a symbol of flexibility, practicality, and economic efficiency. These are the constructions widely known as Quonset huts. Their appearance and use after the war was no coincidence, no temporary solution, but a logical result of the acute housing crisis caused by the global conflict. During those years, when millions of people were left homeless, cities and infrastructure were destroyed, these simple, quickly assembled, and cheaper than traditional structures became a salvation for thousands of families, schools, churches, and even commercial enterprises. In post-war America, there are approximately 700,000 such structures. They were intended for temporary use, and most of them were built in record time, often within hours or days. These structures were originally built as field shelters, military bases, storage facilities, objects that did not require complex technology or significant costs. But precisely in times of crisis, when every government and every family sought ways to survive, these constructions have transformed into something more. They are used to build residential neighborhoods, educational institutions, churches, shops, and even sports halls. In each of these buildings, in each of these spaces, there is not only a necessity, but also a desire for adaptation, survival, and rebirth. The cost of such a structure is approximately $1,000 to $2,500. This is 8 times cheaper compared to traditional brick houses or stone buildings. This factor becomes crucial for millions of families, forced to find affordable housing in the context of a devastated post-war city. In Los Angeles, amidst ruins and new neighborhoods, these simple structures form entire residential complexes, where each house is not only a shelter, but also a symbol of hope. In Portland, under similar conditions, prefabricated structures are used to create small schools where children continue their education despite destruction and economic hardships. In every city, in every district, these buildings serve as a kind of monument to the fact that even in the most difficult circumstances, people seek ways to preserve their lives and dignity. The architecture of these structures is now seen as an example not only of economy, but also of versatility. They symbolize practicality, the ability to quickly deploy and adapt to any needs. Many of them, after years, have gained the status of historical monuments, reminding us of a time when humanity was forced to rapidly find solutions for survival. Their simple construction, assembled from metal frames and fabric or metal walls, is not just an engineering solution. It is a philosophy that teaches. Even in conditions of scarcity and crisis, it is possible to create something functional, sustainable, and durable. Looking more broadly, the use of prefabricated structures is not limited to post-war realities. In the modern world, these principles find new applications. In humanitarian missions, for example, in Haiti after the devastating earthquake at the beginning of the millennium, similar structures are used for the rapid deployment of housing complexes for refugees. From time to time, in disaster or conflict zones, temporary camps appear where such structures allow for quickly providing a safe space for thousands of people. Their technological flexibility and low cost make them indispensable in situations where every minute counts and every dollar matters. But the most remarkable thing is that the ideas embedded in prefabricated structures have not lost their relevance for the future. In advanced scenarios of space exploration, particularly in the colonization of Mars or the Moon, architects and engineers employ principles similar to those of prefabricated structures. In the extreme conditions of space colonies, such lightweight, quickly assembled, and versatile structures will form the foundation for creating living modules or scientific stations capable of withstanding the harsh tests of alien planets. Their simplicity and functionality not only ensure survival, but also create comfortable conditions for long-term existence in environments of microgravity, radiation, and absence of familiar surroundings. The history of Quonset Huts is not just a story of military engineering or temporary constructions. It is a story of how ideas born in wartime find their continuation in various fields of human activity. Their versatility, adaptability, and economic efficiency make these structures relevant even today. They are not merely temporary shelters. They embody a principle that remains alive today, ready to help humanity address global challenges. From natural disasters, where rapid deployment of housing can save lives, to space missions, where every kilogram counts, this is the true value of the idea. This is the main essence of Quonset structures. They are not only part of history, but also part of the future we are creating now, here and today.